Hi, everybody. So now let's use what we've learned about cosets to prove Lagrange's theorem. And as you'll see, it's exactly the properties of the cosets that we worked out, which give us the key insight as to why the order of a subgroup of a group has to divide the order of the group. So here's Lagrange's theorem again. But before we give the proof, let's give a little bit of notation. So suppose H is a subgroup of G, then the index of the subgroup, and this is the notation for it, and notice it's a little bit confusing because the big thing goes on the left and the small thing goes on the right. But this means the index of H and G, and it's the number of cosets of H and G, either left cosets or right cosets. We already know that there's the same number, so you can pick either one and count how many cosets there are, and that's called the index. Now, it can happen that a subgroup has infinite index, and if that's the case, then the index is infinite, so you say H has infinite index. So just to remind you, we worked out some examples. So if H was the group of rotations of the triangle, so if H had 3 elements, this is sitting inside the group of all symmetries of the triangle. So H has 3 elements, and you remember there were 2 cosets. The 2 cosets, one coset was H, the rotations, and the other coset was the set of reflections. So the index of H and G, where G here is the D3, it's the symmetries of the equilateral triangle, the index is 2. If you look at the subgroup NZ, it has index n, because remember the cosets were the sets of the form A plus NZ. A, basically, you can choose 0, 1, up to n minus 1. So there were n cosets, so NZ has index n. And in the case where H had 2 elements inside the symmetries of the triangle, then we found 3 cosets. So the index in this case was 3. And maybe just to give you an example of a subgroup of infinite index, suppose we take for our group G the multiplicative group of the real numbers. So this is the collection of all x in R, which are not 0. And that's a group under multiplication. And let's take for our subgroup H a 2-element subgroup, which consists of plus and minus 1. And this is a subgroup because it's closed under multiplication, right? Minus 1 times minus 1 is 1, 1 times minus 1 is minus 1, 1 times 1 is 1. So what's the index? Well, what are the cosets of H? So if R is an element of R star, then the cosets RH consists of the number R and its negative. And so there are obviously infinitely many cosets because basically you have one coset for every positive real number. If you take an R in R star, R bigger than 0, then you have the coset RH, and they're going to be equal. RH is equal to SH if and only if the sets R minus R and S minus S are equal. And that's if and only if R is plus or minus S. But if we've chosen R and S to both be positive, that happens only if R is equal to S when both R and S are bigger than 0. And there are infinitely many positive real numbers. So this is an example of a group which has infinite index. So it can happen. Now we can state Lagrange's theorem, and actually a slightly improved version of it. I mean, the original version that we stated was that that the order of the subgroup divides the order of the group. But in fact, we can say that the order of the group is equal to the order of the subgroup times the number of cosets of the subgroup. That's what the index is. So it's the order of the subgroup times the index of the subgroup. And so now we not only do we know the fact from Lagrange's theorem, but we even have a name, or we can sort of explain what the other factor is. And here's the idea of the proof. I'm going to draw a little picture. So here's our group G, and here's our subgroup H. And then we have the cosets of H. And the number of cosets is by definition the index. And the number of elements in H is the number of elements in H. And we know that every element of this covers the group perfectly. Every element of the group is in exactly one of these columns, and it occurs in that column only once. So the group is sort of covered by copies of these cosets of H. Each coset of H, well, H itself has number of H elements. There's G index of H and G cosets. The only thing we'd like to know to finish this off is that each of these cosets have the same number of elements in H. And basically, if we knew that the number of elements in GH equals the number of elements in H, then this picture would show us that the number of elements in G is the number of elements in H times the number of cosets. And so let's prove that. And it's actually the simplest way to do it is to construct a map which is a bijection. And we're going to give a bijection from H to the coset GH. And the map is just, it takes an element H and it multiplies it on the left by G. And we're going to show that this is injective and surjective. So it's injective because if f of H1 equals f of H2, that means that GH1 is GH2. And now we multiply both sides by G inverse. We cancel on the left. And that tells us that H1 equals H2 using, we can take G inverse GH1 equals G inverse GH2. So that tells you that it's injective, because if f of H1 equals f of H2, then H1 equals H2. And for surjectivity, we just use the fact that if we have an x in GH, then we know that x is actually equal to GH for some H. And f of H is GH, which is x. So every element of GH is in the image of the map. So all of the cosets are in bijection, so they all have the same number of elements. And so the group is the disjoint union of these sets, the cosets, and each coset has the same number of elements, namely the number of H elements. And so the total number of elements is the size of the rows times the size of the columns in my picture, or order of H times the order of G times H. A couple of corollaries. The first is that the order of an element of a group is a divisor of the order of the group. That's because if G is an element of a group, the order of G is by definition the number of elements in the cyclic subgroup generated by G. And the number of elements in the cyclic subgroup generated by G divides the order of G by Lagrange's theorem. So if you take, for example, Z mod 12, then the order of 3 is 4, because the smallest multiple of 3, which is 0, is 4. And the index, just for the record, the index of 3 of the subgroup generated by 3 is 3, and the order of the subgroup generated by 3 is 4. Another interesting and very general result that follows from this is that if you have a group which has a prime number of elements, then it's automatically a cyclic group. Why is that? Well, if the order of G is a prime number, so suppose the order of G is P, where P is prime, and you take an alpha in G, which is not the identity element, well, then the order of alpha must divide P. And P is prime, and the order of alpha can't be 1 because alpha is not the identity element. So the order of alpha must be P. And that means that the cyclic subgroup generated by alpha has P elements. And the index can only be 1. And what does that mean? It means there's only one coset, and that coset is the subgroup itself. In other words, G is the group generated by alpha. So a group with a prime number of elements is automatically cyclic, and it's more or less a copy of Z mod P. And one other little calculation which can come in handy is if you have a subgroup of a subgroup, then the indexes multiply, kind of in towers. That is to say, the number of cosets of K in G is the number of cosets of H in G times the number of cosets of K in H. And the proof of this is you use Lagrange's theorem to say that the number of cosets of K in G is the order of G over the order of K. That's Lagrange's theorem written, so to speak, solving for the index. And then you can insert an order of H, so it's GH, because the H's would cancel. And then Lagrange's theorem again tells you the order of G over the order of H is the index, and the order of H over the order of K is the index. So the notion, the fact that cosets divide your set up into your group up into disjoint pieces, each with the same number of elements, is essentially what Lagrange's theorem says.